Hello, in this AFNI video we're going to look at a particular kind of alignment, in particular EPI-EPI alignment, so within subject EPI alignment. This is a continuation of the alignment talk where we looked at general principles. So you may have the presentation open up already. It's the AFNI 14 presentation, so you can open that up. And actually I'm going to open up this text file of commands as well, because we will do a little command line processing in vivo here. I'll just turn on highlighting in the text file. Okay, so we'll come back to this later. These are commands we can copy and paste easily. So let's take a look at the presentation. You can see where we're starting in the slides. This particular kind of alignment is useful in addressing motion. So even the best subjects move from time to time in the scanner. If we look at these sagittal images of a typical acquisition of EPI, so time point 1, 2, 3, etc., without motion they all look very similar. When motion occurs, very often we'll see this bright, dark, bright, dark, bright, dark pattern. Why does this happen? Well, our data isn't necessarily acquired, it's usually acquired in axial slices, and they're not acquired kind of slice 0, 1, 2, 3, 4, 5, 6, 7 like that, but they're typically acquired 0, 2, 4, 6, 8, 10, and all the way down, and then 1, 3, 5, 7, 9, which is called an interleaved acquisition. And so if for slices 0, 2, 4, 6, 8, the subject's head is in one position, and then by the time they're doing the next set, 1, 3, 5, 9, the subject has moved a bit, there's that offset results in this bright dark pattern. And we can see that probably the most motion was in this volume, but there's a little bit of the effect here and here as well. If we want to think about this from a time series point of view, what are the motion effects that we can see? Well, let's see. These come from a graph view of 5 by 5 voxels, so there are 25 time series here. And we see the normal kind of up-downness of a time series. But if you notice at this time point in all the time series, there's a very large feature, something kind of outliery that happens, sometimes up, sometimes down, with other bumps and wiggles. And these kind of outliers that get stuck into the time series are hallmarks of motion. Okay, so there's a lot of effects that happen here, things that we want to deal with related to subject motion. And remember also that typical EPI acquisitions have a voxel size of something like 2 millimeter to 4 millimeter isotropic, and 3 millimeter is quite common at 3 Tesla. So we're really talking about a small amount of motion, something far less than even 3 millimeters, that causes big problems for our analyses potentially. So what do? We use 3D Volreg, the main tool in AFNI for volume registration for EPIs across time. And we can estimate, we can basically pick one volume as a reference and then perform alignment to that volume from every other EPI across time. And we get a set of alignment parameters. We're just going to use rigid body parameters, so 3 rotation and 3 translation, because we live in 3-dimensional world. And so for every volume across time, we have that set. How much do we need to translate or rotate that volume to look as much as possible like the reference volume? And that's what's plotted here. And so you can see that we basically have something like a time series of motion parameters. Across all our EPI time series, how much do I need to translate it along the anterior-posterior axis to make it look like the reference volume? Same for all these other parameters, and these are just a box plot summarizing them. Note the units on these are different in each window. Okay, and then once we have these, we can also use these time series themselves as regressors in our GLM model, because these show something about motion. Now, they're not perfect regressors to get rid of motion, because if you remember from this case, sometimes motion causes a spike downward, sometimes it causes one upward, and things like that. So again, these won't fully account for motion. We can also use these as censoring criteria. Basically, we have these 6 numbers, and we can use them to say where do we have large instances of motion in our data set, maybe we don't even trust our data at those points, and therefore we make them into censoring criterion. We can also visualize the effects of motion in terms of the time series in a gray plot. So here we're visualizing the values of our EPI time series across time as height along a y-axis here. And we see something uniform in height changing at all these locations. So we know there's motion. What we can also do is plot our time series as a grayscale across time. In this case, we've stacked all our voxels here, so all 60,000 voxels in our brain, let's say, and across time. And these are normalized values, so kind of z-score values, if you want to think about that. And if you notice across time, sometimes they're pretty small, and then all of a sudden across the same time point here, across space, at this one time point, we run into a very large, either positive or negative feature. And this is a hallmark of what motion does in our time series. So we see these very large spikes up or downward. It's just another way of viewing that. Okay, so let's talk about censoring. How do we find volumes that the data is going to be considered untrustworthy? The first criterion we can use is what's called enorm, Euclidean norm, and this is based on the motion parameter estimates ourselves, our translation and rotation values that align us to one reference volume. So what we do is for each ith volume, so again across time, we're going to use the first difference of motion profiles to calculate enorm. So what does that mean? It means that to calculate the enorm at a given time I, I'm going to use the change in translation along this axis, and this axis. I'm going to take the sum of squares of these first differences and then take the square root of it. So Euclidean norms, this is how they work. It's the same way we calculate distance, where you take the square root of the sum of squares. In this case, it's the difference of motion. Why are we using the difference of a motion parameter and not just the motion parameter itself? Well, consider here, and let's look at this parameter. This is the change along the inferior-superior axis to align to a given reference volume. So here, it's 0 and constant across time, and then all of a sudden, there's a big change in it. So these volumes need a large delta S to align to the reference. And then it's constant again. So that means that the volumes in all of these cases need the same amount of translation applied to look like the reference. That means that even though the motion parameter is non-zero, because it's basically constant across time, it means the subject isn't moving because all of these have to be shifted by the same amount to look like the reference, which means that no motion is kind of happening along here, at least in the inferior-superior axis. Then there's a big motion spike, and then again, it's pretty constant across time, which would mean no motion, etc. So again, this is just to think about why we use the derivatives of motion, because anytime there's a large flat region of a motion parameter, it means the subject isn't moving, because these are all with respect to a fixed reference frame. Okay, so we use this enorm parameter. It's a nice parameter to have. The units of it are what we call kind of millimeters in parenthesis, or something like millimeters. If you notice, we've put in this equation that we're adding together things of millimeters squared and degrees squared, which looks like a poorly constructed formula. However, with the human head radius being the size that it is, 1 degree of motion causes about a 1 millimeter change in the position at the edge of the brain. So therefore, we use this as an approximate measure to put these all here in the same. So if this is kind of a 1 millimeter shift and a 1 degree shift, they have somewhat a similar change in position toward the edge of the brain, where a lot of the brain is. So therefore, we end up with those units for enorm. They're squared, but we take the square root, so it's just millimeters. And then we can set a threshold with a preset value, let's say 0.2 millimeters, 0.3, 0.1, something around there, depending on your data set and acquisition. And wherever the enorm value for a given voxel is higher than that value, then we censor that volume. Now note that since enorm is based on the difference of volumes, so the change in delta p, we know that motion occurred at either the ith time point or the one that we're subtracting with, let's say I plus 1. So we censor both of those volumes because we don't know whether motion occurred in one or the other or both. And actually, a lot of times it's very hard for motion to be constricted to just a single volume. So it often does occur over a larger time interval than would be acquired for just one volume. So anyways, when we're censoring based on enorm, we censor two values because it's based on the differences of these parameters. The second censoring parameter or criterion that we can use is looking at outliers. And let's just go back and think about why that might be useful. We can look here, for example, and if you think about across time, at the same instant in time, I see a big spike. And from this time series point of view, this is probably outlier value, outlier value, outlier value. And so what I have is across space, I get a lot of outliers appearing where there's motion. Or you can look at the gray plot and see it as well. There's probably a lot of, across space, there's a lot of outliers happening here. So what we could do is within a given mask of the EPI dataset, we could count the number of outliers, and that ratio will be between 0 and 1, and that tells us the fraction of outliers in that value. It's a number between 0 and 1, and we can use a preset value, let's say 0.05, which would mean that we'll censor any volume that has 5% or more of outliers in it. And note that we calculate the outliers before we shift and rotate and move around the data set. So this is calculated initially from the unprocessed data. And in this case, it's not a difference between adjacent time points. So we only censor one volume based on this. Okay, with our two criteria of enorm and outlier fraction thresholding, we can plot the parameters here and where would be censoring. So let's say if we censor enorm at 0.2 millimeters, and this is the profile of enorm values, anywhere we go above this line would be censored. And that's what these red bars indicate. This style of looking at it is the way we present the data in the Pythonic quality control for AFNI proc. And here's a histogram, a box plot. So we can see that most of the motion is pretty small, but indeed there are some points that sneak up above here. And for the outlier fraction, again, you can see typically when there's motion, you'll see some bumps up, and then sometimes you'll see big spikes in both simultaneously. And we censor based on the union of the enorm and outlier fraction thresholded censoring. Okay, here's an example we can look at of running 3D volreg, and we can just see the kind of information that we get out of it and how it's used. In general, we won't run this on our own very often because this is something that AFNI proc would do. So we can provide important parameters to it, but then it would be carried out through AFNI proc. So when we're going to perform volume registration, we need to specify one time point, one index, as our base reference volume. So what are we going to compare all the other ones with for alignment? This is an important choice because if this is a bad volume, then all our alignment estimates will be bad. So what would be a good reference to pick? You don't probably want to pick the first one in the scan because the subject may be startled, or there may be pre-steady state things. They may be prone to move toward the end of the scan. It's really hard to say, is 3 always good across all subjects all the time? Well, fortunately, we don't have to make this choice when we actually run with AFNI proc. We can provide a keyword called min outliers to it. And so AFNI proc will look at the set of outlier values, and it will pick the volume to be the reference that has the smallest fraction of outliers. And that's a really nice way of saying what is the most likely candidate volume for not having motion in it, and let me use that as a reference. So in this example, we pick a number. In AFNI proc, we would choose a little bit more intelligently. And when we input our time series, we can see what our motion corrected time series would look like. As we mentioned in the first talk, this is not what we would use in processing, but this can be useful to just visually verify that we got rid of motion. This file will save the motion parameters, the history across time, and this will save the 12 degree of freedom matrix form of them across time. Okay, so that's a description. Let's take a look at this, and the next few slides show these commands to copy and paste. But that is what precisely the set of commands that we have here. So you can open up this text file and follow along. I'm going to just copy and paste each of these lines. I've set up my my home directory here in the standard way for getting ready for a boot camp. So my AFNI data 6 is in the home directory. And so I just moved into this directory where I have data sets. I have this EPI data set, and this is what we'll be inputting to 3D Volreg. Let me just take a look at 3D info on that. And I see here that it has 152 time points, so it probably is a kind of a standard EPI acquisition. The voxel size is about 2.7 by 3, fine. Okay, so this just means seems like a reasonable volume here. Let me take this 3D Volreg command and copy and paste it. If you notice, we didn't specify any cost function. We're just using the default one in 3D Volreg, which is the least squares, and that's a good one for this procedure. It's a very fast program. It finished aligning 152 volumes in the amount of time that I was rambling there. Okay, let's take a look at the output motion estimates. So they're in this D file here. I'm going to copy and paste this. It's a 1D plot command, which is useful for looking at data sets. The Volreg option means that here you'll see here what Volreg does. It just helps us identify what each row and column are. The SEP scale option was used, so each of these plots for each motion parameter, the 3 translation and 3 rotation, has its own scale. All right, if we look here along these motion estimates, we see that it's kind of bubbling along here with not very large values. Typically here, though, what do we see? Well, actually, there's something here with a value out to about -2 millimeters like that. So it's kind of constant, then boom. And if you remember, we looked at this data previously, and let me just underlay the EPI. And if I open up a graph time series now, and if I hit the V key to scroll through in video mode, just watch the sagittal image, and there, hopefully you saw what just happened there. Let's find a voxel here. Okay, so if I go along in time, you can see that there's some kind of motion event there. I'm going to close these other windows just briefly. Okay, so that makes sense of what this spike is. It's this in the pitch, which is the nodding direction where that large motion event took place. And I've lost, there we go. Okay. And what I could also do is I could look at this VRT, which means Volreg for time, so the motion corrected data set. I'm just going to open up a new window quickly and open up the sagittal image for that and make it this EPI R1 VRT. Okay, and if I go to define data mode here and lock, I can choose to time lock the data set. So they were already spatially locked if I move around the crosshairs, but now they're time locked together here. So if I choose the time index, you'll see they're both changing, but you'll see that the top one has a motion event and the bottom one doesn't really. Okay, now one thing you will notice actually is that there's some smoothing here. And again, because this had to be aligned, we talked about the relation that smoothing will always occur whenever we're interpolating data a lot. But anyways, you can see that the motion estimate was pretty good because it looks constant across time. Okay, something else we can do is this next copy paste here. We can, oh, we already looked at that. If you want to see the raw file for here, so this is what the 1D parameters look like. They're just a file of 6 columns of numbers here. Each one is a translation and rotation across time, so there should be 152 rows. If you look at these numbers, they're all pretty small, plus and minus. However, there's one of these rows that looks a little bit special. See if you can spot it. All right, did you pick out this one that was all zeros? And why is that? Well, remember that in AFNI, we start counting at 0. So this is time row 0, 1, 2, 3. And if you remember, the index 3 volume was our chosen reference. So it makes sense that there's all 0 translation and rotation parameters for that volume. Okay, so that just is consistent. Here we can look at a quick enorm calculation. Okay, and in this case we set the threshold at 0.3, so 0.3 millimeters, and it tells us there were 6 values above that. We can plot the results of that along with that threshold at 0.3. So there you go, that's the command to generate this plot, and here's the threshold, and you can see there are some values here and here, and these are the indexes. Fine. Okay. This is the AFNI sub-brick selection for this time series of where the motion occurred, if you see that. So this would be basically an option that could be presented into this command here. And now this is a way to combine the same information that we just looked at of the plot with where there should be bars of where the censoring occurs. Okay, so again, this is all explained here, and you can look at that. Fine. Okay, now there are some caveats with all of this. We need to acknowledge the fact that we talk about motion correction, but I really don't like this term. We cannot fix motion in the sense of making it look like our data set never had subject motion in it. So if you give me data from someone who moved and data from the same person who didn't move, I can't make the results be exactly the same, the fact that if motion never occurred. We can use motion regressors in our model, but again, as we've seen, the spikes go up or down in ways that really can't be predicted, and so we can't really get rid of these effects. We can censor the data. That helps a little bit mitigate some effects. We can perform alignment, so geometrically we correct for some of the effects, but when we perform that regridding of the data, there will be some smoothing due to that. It's really important to note that just because 3D Volreg ran and gave you an output of results, you should always verify and check things. And here's an example case of a macaque study here. In this particular study design, the monkeys received juice at stimulus time, okay? And they have really large jaw muscles. So here you can see that their jaw muscles and the brain. So if we just perform 3D Volreg on this data, you can see that there are spikes in it, and the output, well, it still looks like it moves around a bit. I can see motion in the brain moving, and I still see spikes. Does this mean that 3D Volreg doesn't work on monkey data? No, that's not true at all. What's happening is 3D Volreg doesn't know to treat the brain differently than these jaw muscles, so it's just aligning everything in the field of view, and it's got these big, bright jaw muscles here, and so it's working to align that. If I were to mask the data set first and then perform alignment, now you can see that the brain really moves around a lot less, and these spikes are also quite a bit more mitigated. This just goes to show that you really have to be careful about your data. The program doesn't make any assumptions. It won't try to be able to help you or point out, oh, there's something extra here. No, it just it can't do it, so it's up to the user to check. It's also up to the user to make careful study designs so that you don't have stimulus-correlated motion. In this case, since the monkey gets juice every time that there's a stimulus on, their jaws are going to move, taking in the juice through the straw. Now you're going to really have a problem that your motion regressors are going to be highly correlated with your stimuli, and you're going to run into modeling problems as well. So how do you want to think about fixing motion? It's really hard. We do things like regressing out some factors and having Euclidean norm for censoring and things like that. But again, it's very difficult. The experimental design that you choose is probably the most important thing that you can do to help yourself with motion. So even before you're scanning someone, come up with a study design that will try to have minimal amount of motion overall, and certainly minimal amount of motion that would be associated with your stimulus. So don't have kids wave their hands in the scanner as part of their stimulus, because then they're just going to be having highly stimulated, task-stimulated motion. If you're interpreting results across groups that have different amounts of motion, you have to be very careful. For example, if you're studying groups with ADHD and typicals, then one group might be expected to move more than the other, and you have to try to make sure that your results don't depend on motion. It's a very hard thing to do, so you have to do extra work to quantify motion and to show that it's not associated with your results. Okay, just to note that this isn't particularly related to motion, but another case of EPI-EPI alignment comes up in the case of performing EPI distortion correction. So this is work that Bob did working with Vinay Rupchan at NIH to put in EPI distortion correction when people have what are called blip up, blip down acquisitions. So this is a little bit more specialized than we'll get into here, but basically along the phase encode direction of any EPI dataset, you see a particular kind of distortion due to the fact that EPI field, the B0 field, is not perfectly homogeneous. And what you can do is you can acquire datasets where the phase encode direction goes this way and ones where they go in the opposite way, and then use the relative amount of distortion with alignment to try to estimate the geometric effects and undo that distortion. So here's an example case with data from Vinay and implementing it. There's also a new tool in AFNI for using B0 corrections if you have phase distortion, again through work with Vinay. So if you have the uncorrected EPI as the underlay, and here's the corrected one. Anyways, these are just kind of advertisements. That's a separate discussion than motion correction. Okay, so finally, here's just a summary of slides about motion. The one thing to remember is you really can't correct for motion and get rid of all the bad effects of it, either geometric or time series, but there are a number of things you can do to try to reduce some of the effects in your time series. In resting state, it's probably a bigger problem than task data, because in task data, at least you have beta weights to focus on. In resting state data, all you're left with are the residuals, so you kind of get rid of all the stuff that you think is bad, and you have the remainder. In task fMRI, you get rid of bad stuff, and then you also try to focus on something particular. So you really have to be careful with your study design. This is a large topic in the field and has been for many, many years, and somehow still seems to be. Sigh. Global signal regression is really not a recommended way to get rid of motion. There have been a lot of papers published on it, and we've shown mathematically many times why it's wrong to do, or why it leads to hard to interpret effects in the data. It strongly changes your data just with performing global signal regression. And anyways, here are papers that can be looked at for this. G-core is a more palatable way to try to deal with motion effects at the group level. And again, the most important thing you can do for motion mitigation or correction is study design. Make sure your subjects are used to being in a scanner and take into account all the effects ahead of time that you can. It's much easier to mitigate than to try to solve the problem later. Thanks.